Yeah, let me start this class with a question to you. Please, do you know how many conformers are possible with ethane? And can you identify which is the most stable one among the possible conformers? Okay, just think on that. Today, I want to teach you on study of conformers in ethane. Study of conformers in ethane. So ethane molecular formula CH3 and CH3, right? This is the molecular formula, chemical structure of ethane. This you can write like this. Okay. So suppose if you view this molecule, if you observe this molecule from this side, so then this would be the front carbon, and this would be the rear carbon. Okay. So as I explained you previously, that front carbon can be denoted with the dot and the rear carbon, right, with the circle. Okay. So three hydrogens on each carbon. So one hydrogen, another hydrogen, and another hydrogen. Okay. These hydrogens and these bonds have 120 degrees bond angle, right? And the rear carbon, okay, the rear carbon, you have hydrogen like this, hydrogen like this, hydrogen like this. Okay. What is the dihedral angle in between these two planes? Okay, dihedral angle can be denoted with theta and 0 degrees. Okay. So therefore, this conformer is called eclipsed conformer, fully eclipsed conformer. Fully eclipsed conformer. If you rotate CC single bond, this CC single bond, if you rotate 60 degrees, you will get so this is the staggered conformer. Staggered conformer. Okay, if you rotate again 60 degrees, you will get eclipsed conformer. If you rotate again 60 degrees, that means 180 degrees, then you will get staggered. So if you rotate 60 degrees, so finally you will get two kinds of conformers in the case of ethane. Okay, so one is eclipsed conformer, the another one is staggered conformer. So which one is more stable? If you want to identify, or if you want to explain about stability, you need to know the 7 factors which I told you in the first class, which can influence the stability of different conformers. Okay, what are those? Can I remind you those 7 factors which can influence the stability of conformers. Okay, the first factor is eclipsed strain or fissure strain or torsional strain. Okay, any of these three uh, can you can pronounce it, or you can write it. Okay, either eclipsed strain or torsional strain, fissure strain, all of them same strains. Okay, and what is the second factor which can influence the stability of different conformers? The second factor is van der Waals repulsions. Van der Waals repulsions. It may be van der Waals attractions or van der Waals repulsions. Okay, van der Waals interactions. In van der Waals interactions, you have van der Waals repulsions and you have van der Waals attractions. Okay, van der Waals attractions contribute the stability to the conformer. Van der Waals repulsions contributes instability to the conformer. Eclipsed strain contributes distability to the conformer. Okay, and dipole-dipole interactions, dipole-dipole repulsions also contributes instability or to the conformer, and intramolecular hydrogen bonding, which contributes stability to the conformer, and hyperconjugation. Hyperconjugation contributes stability to the conformer. If hyperconjugation possibility is there in the conformers, then hyperconjugation plays important role. Okay, that's how you can decide the stability of different conformers. Finally, geminal repulsion, geminal repulsions. Okay, so if two bulky groups exist on the same carbon, then there is a repulsion in between those two bulky groups. That's how it contributes instability to the conformer. Okay, so those are the factors which can influence the stability of different conformers. In this case, it is eclipsed one and the staggered conformer. In eclipsed conformer, you have eclipsed strain or torsional strain or fissure strain is exist because of this eclipsed conformer. Okay, and in the case of staggered conformer, there is no eclipsed strain, there is no steric strain. Okay, so because in between the hydrogen bonds, because the dihedral angle is 60 degrees, so there is no question of steric strain or any eclipsed strain in staggered conformer. Therefore, staggered conformer is more stable than the eclipsed conformer. Okay, so I am going to draw the potential energy diagram for this. Potential energy diagram for ethane. Potential energy diagram. Potential energy diagram. So on y-axis you can take energy, okay, in kilojoules per mole. In kilojoules per mole. On x-axis, dihedral angle. Dihedral angle. Nothing but theta. Okay. So is 0 degrees, 60 degrees, 120 degrees, 180 degrees, 240 degrees, 300 degrees, finally 360 degrees. Okay. So at 0 degrees, that means it is eclipsed conformer. So eclipsed conformer has more. So suppose you take this is as arbitrary 0 level of the conformer, okay, energy. Then eclipsed at 0 degrees, dihedral angle, it has like this, and comes down at 60 degrees, and at 120 degrees it goes up same way, and 180 degrees it is staggered, therefore comes down. 240 it is eclipsed, then 300 it is staggered, then okay, right, like this, okay. At 0 degrees dihedral angle, that means eclipsed, the eclipsed conformer has about 12.5 kilojoules per mole energy, potential energy. 12.5 kilojoules per mole potential energy at 0 level, at 0 dihedral angle, and when it rotates 60 degrees, that potential energy comes down to 0. Then if you rotate again 60 degrees, that means 120 degrees, then it will become eclipsed, therefore again it has 12.5 kilojoules per mole energy. And if you rotate another 60 degrees, that means 180 degrees, so that it will come down to 0, and 240 it will be eclipsed. At 300 it is staggered conformer. At 360 degrees it is eclipsed conformer. So all at 0, at 120, at 240, at 360 degrees, all are eclipsed conformer. Dihedral angle 0 degrees, 120 degrees, 240 degrees, and 360 degrees. All are eclipsed conformers. Eclipsed conformers, therefore they are less stable and more energetic. So what about dihedral angle at 60 degrees and 180 degrees and 300 degrees? It is staggered conformer. And in staggered conformer, it won't have any eclipsed strain and any steric strain or any van der Waal interactions in that. All are absent. So because of that, staggered is more stable, less energetic and more stable than the eclipsed one, which is less stable and more energetic. It has more energy, 12.5 kilojoules per mole. And about this staggered one is, we can take it arbitrarily as 0 degrees, 0 kilojoules per mole, okay. So this is the potential energy diagram of ethane conformers. Ethane molecule has only two conformers. One is eclipsed conformer, the another one is staggered conformer. Eclipsed conformer has eclipsed strain and also steric strain in that, so that it contributes energy to that conformer, so that it has high energy, 12.5 kilojoules per mole. In the case of staggered, there is no eclipsed strain because the bond angle, the hydrogens, and there is no question of bonded or non-bonded interactions or repulsions in that molecule, in this conformer. Therefore, staggered conformer is more stable than eclipsed conformer. Okay, this potential energy diagram is known as sinusoidal diagram. Okay, this kind of diagram can be known as sinusoidal. Okay, so this kind of waves or this kind of diagram, okay, can be called as sinusoidal diagram. Okay, sinusoidal. So this is about ethane conformers. Okay, next I'll explain you about ethane. Now ethane is over. 1,2-di substituted. Study of conformers in 1,2-di substituted. 1,2-di substituted. Ethane derivatives. 1,2-di substituted ethane derivatives. So I'll give you the best example for this. CH3, N-butane. N-butane is one of the example for 1,2-di substituted ethane derivatives. Okay, so shall we work out what how many number of conformers possible in N-butane and which one is more stable? So you need to find out. Okay, suppose if you view this molecule from this side, so this is the front carbon, and this would be the rear carbon. Okay, rear carbon. So I'll try to write the possible conformers for this. Okay, circle means rear carbon. This dot means front carbon. Okay, front carbon has one CH3 group, two hydrogens. One CH3 group, two hydrogens. Okay, so these three bonds have bond angle 120 degrees. Okay, and what about the next one? The same one is so this is rear carbon. So at 0 degrees. Okay, at 0 degrees. That means this is fully eclipsed conformer. Fully eclipsed conformer. If you rotate 60 degrees, the CC bond, 60 degrees, you will get different one. This front carbon substitutes or attached ones, you keep it same, and you can change these rear carbons atoms. Okay, CH3, hydrogen and hydrogen. So this is the Gaussian conformer. Gaussian conformer. Okay, or as I told you yesterday class, according to Klein and Prolak terminology, it can be shown as plus SC conformer, plus SC conformer, because it is thin and cleanal, 60 degrees. Okay, so again you rotate 60 degrees this one. What happens? That means you will get this kind of conformer. Hydrogen, hydrogen, CH3, here CH3, hydrogen and hydrogen. So this is partially eclipsed conformer. Partially eclipsed conformer. So this can be according to Klein and Pralag, how we can write 120 means plus AC, anti-cleaner plus AC, anti-cleaner. Okay, again you rotate 60 degrees, you will get CH3, hydrogen and hydrogen, CH3, hydrogen and hydrogen. So this is staggered conformer. Staggered conformer with bond angle is 180 degrees. Okay. So this is this can be shown as plus or minus AP. This is plus or minus SP. According to Klein Pralag terminology, we can denote like that. At 0 degrees, plus or minus SP. At 60 degrees rotation, it is Gaussian conformer. The bond angle between these two planes is 60 degrees. Therefore, it can be denoted as plus SC. S means sin, C for cleaner. Okay. Again, you rotate 60 degrees. That means total 120 degrees. You will get partially eclipsed conformer. Again, if you rotate 60 degrees, the total 180 degrees. So you will get staggered conformer or anti-conformer. This is also called as anti-conformer. Staggered and or anti-conformer. So these four kinds of conformers possible. If you rotate again 60 degrees, this staggered conformer, what happens? This CH will come here, this H will go there, and this hydrogen will go here. That means partially eclipsed conformer. Again, if you rotate 60 degrees, single bond, what happens? You will get Gaussian conformer. Again, if you rotate 60 degrees, you will get eclipsed conformer, fully eclipsed conformer. Here, two types of Gaussian conformers present. One is P Gaussian and about 60, that means 240, 300. At 300 degrees rotation, you will get M Gaussian. About 60 degrees, you will get P Gaussian. About 300 degrees dihedral angle, you will get M Gaussian. Okay. So these are the possible conformers for 1,2-disubstituted ethane derivatives like N-butane. Okay. So next, I'll try to write the potential energy diagram for this. So let us talk about the stability factors in this structure, in these conformers. So if you take eclipsed conformer, fully eclipsed conformer, so there is a eclipsed strain, and there is also steric hindrance in between these CH3 groups because they are two bulky groups, and van der Waals repulsions are there. Okay, and van der Waals repulsions are there. And what about this? And in this non-bonded electrons repulsions also exist in this. What about this? So there is no eclipsed strain. There is no eclipsed strain there is no steric hindrance, there is no van der Waal repulsions in this, because each groups and atoms separated well, therefore there is no van der Waal interactions in between them. Therefore Gaussian conformer is stable than the eclipsed conformer. So what about partial eclipsed conformer? It has also eclipsed strain and steric hindrance, van der Waal repulsions are there in this, in between CH3 and hydrogen. So there is van der Waal repulsions and steric hindrance and eclipsed strain. All these are present in this partially eclipsed conformer. Therefore, so if you compare these fully eclipsed and partially eclipsed conformers, fully eclipsed conformer, in fully eclipsed conformer CH3 groups, two CH3 groups are very nearer to each other. In this partially eclipsed conformer, CH3 and hydrogen little bit low eclipsed strain than to fully eclipsed strain. Okay, so therefore this is high energetic, the second one is this, and the third one is this. And if you look at this staggered or anti-conformer, in this two CH3 groups are well separated with 180 degrees dihedral angle. Okay, so therefore there is no chance of eclipsed strain or any steric hindrance or any van der Waal interactions or any van der Waal repulsion in between them. Therefore this staggered or anti-conformer is more stable than Gaussian conformer and is more stable than partially eclipsed conformer, and finally the very less stable fully eclipsed conformer. This is high energetic. Energies are reverse. It has high energy, then this, and finally this. So among these four conformers, this would be the stable one because it has very less energy. Therefore it takes arbitrarily zero energy. With that we can draw the potential energy diagram for N-butane. Potential energy diagram for N-butane. So now I'll explain you through potential energy diagram. On y-axis you can take energy, potential energy, kilojoules per mole, and it is the dihedral angle. Okay, at 0, 60 degrees, 120 degrees, 180 degrees, and 240 degrees, and 300 degrees, and 360 degrees. Okay. As I explained you through structures, fully eclipsed conformer has more energy. Approximately it has 18 to 25 kilojoules per mole. Okay, if you take this energy is 0, arbitrarily take 0 at this. Okay, now 0, so more 60 degrees Gaussian, then 120 partial eclipsed, then very stable this one, then partially eclipsed, then Okay, so this is the potential energy diagram for N-butane. So here it is 60 degrees. At 60 degrees it has same 3.3 kilojoules per mole energy. Kilojoules per mole energy. Same thing. It is 0 degrees. 0 kilojoules per mole. Okay. So partially eclipsed conformer has 14 kilojoules per mole. 14 kilojoules per mole energy. Fully eclipsed 18 to 25 kilojoules per mole energy. Partially eclipsed at 120 and 240. So they have 14 kilojoules per mole energy. And this is 0. Okay. And 360 same with the 0 degrees. Okay. So this is the potential energy diagram for N-butane conformers. Okay, N-butane conformers. So this is fully eclipsed. This is P Gaussian, and this is partially eclipsed. This is staggered or anti-conformer, and this is partially eclipsed, and this is M Gaussian conformer, and finally at 360 degrees it is fully eclipsed conformer. Okay, so this is the non-sinusoidal diagram. Non-sinusoidal diagram. Okay, non-sinusoidal diagram, potential energy diagram. Previously in ethane, sinusoidal diagram. Okay, so this is about N-butane conformers and stability order. Stability order, how we can write? Staggered conformer is less energy, therefore staggered is more stable than Gaussian, is stable than partially eclipsed, is stable than fully eclipsed. So this is the stability order in N-butane. This is the stability order in N-butane. Okay. Next, let us try to